In previous lectures, we have talked about using functions from the scipy.integrate submodule to calculate integrals of one variable. We have looked at the Sims method, we have looked at traps. These are for Simpson's one-third and trapezoidal rule respectively. We have also looked in great detail at the quad function which carries out Gauss quadrature. We have also taken a look under the hood and discussed exactly what kind of adaptive Gauss-Cron-Rod quadrature is really carried out by the quad function and so on. In this lecture, we are going to talk about how to use functions available in the scipy.integrate submodule to calculate multiple integrals. So, in fact, the submodule gives you utility functions which allow you to calculate double integrals, triple integrals, even integrals over arbitrary number of variables. So, let us start with the double integral calculation. Just to remind you, when you calculate a double integral, you integrate a function f of y and x, say first over y, from limits which depend typically on x, so from g of x to h of x, and then this resulting thing is integrated over y, over x. So, pictorially you depict it this way, that g of x and h of x essentially give you boundaries of the region, this intervening region here, over which the integration is carried out, and the way I have spoken it, and in fact the way this has been written, sort of obvious that you do the y integral first, and after you carry out the y integral, you carry out the x integral. So, this is really an iterated integration. You carry out the y integral first, as I said, for a fixed value of x, and the range or the limits for the y integration is decided essentially by the value of x through the function g of x, which gives you the lower limit, and h of x, which gives you the value of the upper limit. Of course, when you calculate this whole thing out, you get a function of x, and this function of x is then integrated out over x to essentially give you the final integral. Now, you might feel that I have done something slightly unusual here, which is I have written the integrand f as a function of y and x. Usually you would be used to seeing f written as a function of x and y. The order here seems a bit strange, and the reason for this is as follows. The double quad and the triple quad functions that we are going to meet soon of scipy.integrate insist that the arguments of the function go in the order in which the integration is carried out. So, here notice that the way we have written this, is obvious that this is a nested integral with y integration carried out first and then the x integration carried out, and for that you have to see here y integral is being carried out first. So, the function is defined with its first argument as y and second argument as x. In a 3D integral, if you were to carry out the z integral first, then the y integral, then the x integral, then the integrand has to be written down as a function of z, y, x. So, this is one thing which you have to bear in mind. The order in which the arguments are written in the function in the double quad or the triple quad functions that we are going to meet, the order in which the integrand's arguments are written is the order in which the integrals are carried out. So, as an example of this double integral thing, let me consider this particular integral. It's an integral of x square y, the integrand, over y first, then over x, and the limits are given as x to 1 for y and 0 to 1 for x. And it's easy to see that this means that this is the region, this triangular region is the region over which the integral is being carried out. So, the limits for the y integral for a given value of x goes from the current value of x to 1, the upper limit. And as x changes, of course, this blue strip here becomes longer or shorter depending on which way you are moving. And for when x goes all the way from 0 to 1, it traces out this particular triangular region. Now, of course, you can do the integral the other way around as well. You can do the x integral first, which means for a fixed value of y, x will go all the way from, well, this is wrong, this should be x equal to 0, so I am sorry for the mistake here, from x equal to 0 to x equal to y. So, you go from x equal to 0 to x equal to y, as you can see correctly in the limits here. In the figure I have just written it wrong, and then y integral is carried out from 0 to 1. Both of these should of course give you exactly the same answer, and the integrals are very easy to calculate by hand or even orally if you want. For example, this integral for a fixed value of y is simply y into y cubed by 3, that's y into y to the 4 by 3 after you substitute the limits, and then when you integrate that over y from 0 to 1, you get 1 over 15. So let's see how you would calculate this integral using the double quad method. Of course, the first step in doing the calculation would be to import scipy.integrate as SI. I've also imported numpy as NP. I'm not going to really be, am I going to use numpy? I'm not sure I'm going to use numpy for this particular calculation, but force of habit, you know. And now the first thing you need to do is define your integrand. And here I've used a lambda method to define the function of y and x. But note carefully, I've defined f to be a function of y and x with y as the first argument, x as the second. Of course, its value is x square into y. So it takes y as the first argument, x as the second, and returns x square y as the value. So this is a function, the integrand function. Now comes the usage of the double quad function. For double quad, what you need is of course several arguments. The first one could be the function of name of the function that you are integrating. It's just like quad. In quad, you needed the name of the function, the lower limit, the upper limit, at the very least. Here, what you need is the name of the function. Then comes the limits, but now you have 4 limits to talk about, those for x and those for y, and this might be slightly confusing, but you have to remember it anyway. The order in which the limits are supplied is the same as the order in which you write it here. So while the order in which the integrand's argument has to be given is the order in which the integration is done, that is y first, x next. The order in which the limits are supplied is basically the outer limit first, 0 to 1, then the inner limit. The inner limit of course has to be functions of x in this case. So this is basically how you do it. The function name is dblqad, then you have the function f, the name of the function, that is integrand function that you are integrating. Then comes the lower limit for x, 0 in this case, upper limit for 1, limit 1. Then comes the lower limit for y, which is a function, and I could have defined the function outside first, but for functions which are as simple as this, you can just define the function within the double quad call itself. I've just said lambda x maps to x. That of course is what this function is. And then the upper limit, which is just a constant, I put in 1. As you can see, this calculation has been carried out, and you have got 0.0666, which is 1 over 15, with this as an error estimate. Just as quad gives you the value of the function, the integral and the error estimate, double quad does the same thing. It's really running quad under the hood, so this is not surprising. Now, let me warn you that if you are using a slightly older version of scipy, then it would have insisted that all your inner integrals limits must be functions. So using this 1 here would give rise to an error. Then in such cases, if you are using an older version of scipy, Of course, one good way around that would be to upgrade your scipy, but if you can't do that for some reason, in such cases what you have to do is apply even 1 as a function. That's not difficult to do. All you have to say is lambda x space x colon 1. So a function which you are defining, which takes in as an argument x, returns 1. Fine. So this works perfectly. Just to remind you, double DBL QED, name of the integrand, then 2 numbers which give you the limits for the outer integral. These are of course numbers, and then 2 functions which give you limits for the inner integral. Here, because the upper limit was a constant, I just put in a number, and this will work for newer versions of scipy.integrate. Now, can we do this in the other order, x first, y next? Well, just to remind you, if you are doing this in the other order, this is what the limits look like: 0 to y for x and 0 to 1 for y. So let's try that. So I calculate the same thing. I run the double quad function, the function f, then goes 0, 1. These are limits now of y, by the way, not of x. Then 0, the lower limit is a constant. Then I put in a function which maps y to y. Unfortunately, the result which comes out immediately doesn't seem to match. You're getting 0.1 and not 1 over 15 as you expect. You're getting 1 over 10. So what went wrong here? If you have been paying attention, it would be easy to understand what went wrong. I have been saying this over and over again. In the integrand, the first argument should be the integral over which the integration is done first. So because we did an integral over y first before, we defined the function f as 1 with y being defined as the first argument, x as a second argument. Of course, the result is x square y. Here, unfortunately, I am trying to do it in reverse order, x first, then y, but I forgotten to change the function itself. The function is still one in which y is the first argument, but that will work only if you were doing the integration over y first. Now, I will let you worry about exactly what function is it that, what integral is it that double quad actually calculated here, and why did you really get a value of 0.1. You should be able to figure that out yourself. But to do it right, what I need to do is define a new function, let's call it g. It has the same value x square y, but has x as the first argument, y as the second. So the order in which I am doing the integration. If I do that, I get exactly the same result this time as the correct one, 1 over 15. Now here, of course, you have integrand had only 2 arguments, x and y. If you had more arguments, x, y, say some parameters a and or b which you may want to change and so on, then you would have to play the same kind of trick that we did with quad. Quad, remember, only integrates over one variable, supplies one variable by default. The other value, other arguments to the integrand function have to be supplied via an optional argument to the quad function called args. So when you write args equal to and a tuple equal to tuple, the tuple will contain all the values which you want to put in. So in this case, for double quad, of course, the integration is done over 2 arguments, first over y, then over x, or first over x, then over y, whichever order the arguments are written in. And then once you do that, you actually end up with the result, provided the function, the integrand function does not have more arguments. If you have more arguments than 2, you would have to supply the values of those arguments using the args option or the args argument of the double quad function. So that's all about double integrals for the time being. The rest of the double integrals story, like things like other optional arguments which a double quad takes is rather similar to the quad situations. I am not talking about them again. I will just show you briefly how to do a triple integral. Well, a triple integral, of course, is an integral over a function of z, y and x. Notice the order in which I have written down the variables here is the order in which the arguments have to go in your triple quad integrand function. The z integral is done first, then y integral, then x integral. That's the order in which the arguments should occur in the integrand's argument list. Of course, the z integral is done from a function of k of x and y to a function j of x and y. Once you do this, the resulting thing is now a function of x and y, which is now integrated over y from limits over limits which depend on x, and then finally you are integrating over x. Of course, you could have done it in some other order, and sometimes it's more convenient to use it in some other order, but this is just one way of doing it. The other ways you can figure out yourself. So let's just say we are going to carry out this integral. The integrand here has not been written at all, it's just 1. And if you think about it a bit, this really is something which integrates 1 over the region of space where z goes from minus root over 1 minus x square plus y square to plus root over 1 minus x square plus y square for fixed x and y. But then x goes from square root of minus root over 1 minus x square. There is a typo here, the upper limit should be 1 minus x square. That's negative of this 1. And then from minus 1 to plus 1 for x. So think about it a bit, this is really nothing but the integral of 1 over a sphere in 3 dimensions, so sphere of radius 1 in 3 dimensions. And the value is of course the volume of the sphere, which is 4 pi by 3. So let's just check whether that's what comes out. So we are going to use the triple quad TPLQUAD function for this. And here, of course, the bare minimum that you have to arguments that you give is first the function which you are integrating over, the name of the function, then the limits in the order in which you have written them here. So the limits of x first, then the limits of y which are function of x, then the limits of z which are function of x and y. So what we have done, just to make the later writing less cumbersome, we have defined function g of x is minus square root of 1 minus x square, and despite the typo here I actually did it right in the actual program. So h is defined as a function of x which maps to plus square root of 1 minus x square. Then you have j, which is the lower limit. So j is the upper limit. So you have k here, which is the lower limit for the z integral, is minus np dot square root 1 minus x square minus y square, and j is the upper limit, which is this one. So we have defined these 4 functions. You can just use names of those functions in the actual call of triple quad instead of actually having to write the use the lambda functions there. So you can call the triple quad function from the SI. Remember, that's our shortcut for scipy.integrate. So SI dot triple quad. Then I need to give you the integrand. Here the integrand itself is not defined because it's simple, it's 1. But remember, it has to be given always as a function. So what we do is we define lambda z comma y comma x, the order of the variables, remember, has to be whichever one you do first, then the one, then the other. In this case, because the integrand is independent of z, y, x, it doesn't really matter, but in general it would have mattered. So the order in which the integration is done, in that order I am writing them down. But the limits have to be given in the order in which you write them here. So minus 1 to plus 1 first, then sorry, this is the minus. Okay, this one I was a bit confused for a while because I was thinking that it's 1 to minus 1, but no, this one is part of the function definition. This is the function integrand defined here. Then the limits are minus 1 to plus 1. Then from g to h, gx to hx, g is of course this function, h is this function with the sign corrected, and then from this function k to this function j. So GHKJ. And if you do it, you get 4.18879 as your answer. This is of course the error estimate. Just to see whether you got it right, what I do is I divide this result by pi, the result I have received by pi, and multiply by 3 by 4 to see whether I am getting 1. Of course the result itself cannot be divided by pi or anything, because it's a tuple, and tuples of course cannot be multiplied or divided by numbers. What we are doing here of course is taking the 0th element of the tuple. The underscore, remember, just gives you the last result. So the last result was this tuple. Underscore square bracket 0 gives you the first number of this tuple. You're multiplying by pi, dividing by pi, and multiplying by 3 by 4. And the result, as you can see, is 1 to a very high degree of accuracy. So triple quad really gave you 4 pi by 3. For more complicated functions, you will be a bit more careful in defining the integrand and so on, but this is basically the way in which the whole thing is used. I'm not going to discuss n-dimensional integrals here. You can look up the n-quad documentation if you want to. Just remember one thing: if you are using n-quad to calculate very high order integrals, it may be a good idea to change the epsprel or epsprel or the epsaps arguments, which talk about how much error you can tolerate, to less restrictive values, because the higher the dimensionality of the integral, the more and more the time required will be. That has nothing to do with Python or NumPy or scipy. It's basically the way higher dimensional integrals are. The number of evaluations needed at the same error level increase exponentially with dimension. So if you are interested in the n-quad, just look up the documentation. It's pretty easy to understand, and it should be easy to understand after you've gone through this video. Bye for now.